Hi everybody, and welcome to Tropical Meteorology, Atmospheric Science 470 and 470G for the graduate students this semester. So this is the first in a series of videos that'll take us all the way through this semester. This is the first of 3 videos for our section on the climatology of the tropics, focusing on features from the equator all the way up to the subtropics, the interface between the tropics and the mid-latitudes. So in this particular video, we're going to cover how we can define the tropics. And once we've considered several definitions for how we can define the tropics, we're going to take a look at some controls on surface temperatures within the tropics. So here's our first definition for the tropics, and it's a fairly simple one. It's the range of latitudes where the sun can be directly overhead at any point during the year. So we know as the seasons progress, we have the sun directly overhead of the Tropic of Cancer during the summer solstice in the northern hemisphere, and then we have the sun directly overhead of the Tropic of Capricorn during our winter solstice, which would be the southern hemisphere's southern solstice. So these range between 23.5 degrees north and south latitude. So we could define the tropics basically as any place where the sun can be directly overhead at some point during the year. Now this orientation to the sun, where it's always directly overhead somewhere between the Tropic of Cancer and the Tropic of Capricorn, means that these areas are going to experience direct sunlight throughout the entirety of the year, which, as we'll show, leads to a lot of similarity in terms of temperatures throughout the year within this region. So now we're going to take a look at a slightly more complex definition here. This one is the range of latitudes. So again, we're looking at a band of latitudes from south to north, where the net annual absorbed radiation, whether that be radiation from the sun, what we would call shortwave radiation because it comes in at short wavelengths given the very high temperature to the sun, or radiation that is absorbed and re-emitted toward the surface within the atmosphere, what we would call long wave radiation, because it occurs at long wavelengths given the relatively cold temperature, at least versus the sun, of the Earth and its atmosphere. So where the net annual absorbed radiation is greater than the net annual emitted radiation, radiation that's lost to space, being emitted by the Earth's surface and or its atmosphere and being lost to outer space. So there's a range of latitudes roughly between about 35 to 40 north and south degrees latitude where there is a net surplus. That which is incoming or is absorbed exceeds that which is lost to outer space. Whereas at higher latitudes, toward the North Pole and toward the South Pole, there's a net deficit. Granted, as we go through the course of the semester, we'll talk about the atmospheric circulations that try to minimize this imbalance. This imbalance here would create a very large temperature difference between the equator and the pole that is larger than what we actually observe. So there are circulations that help to counteract this surplus versus deficit. However, one way of thinking about the tropics would be very similar to that from the previous slide, related to the sun, and in this case, how much radiation, rather than just how much is directly overhead at any given point of the year. So this is a little bit wider of a definition for the tropics, and probably a bit wider than most of you would think when you think about the tropics. 35 degrees north, 35 degrees south. By the time you're getting to 35 north, you're looking at somewhere around Oklahoma, toward the Carolinas, central California. These are fairly high latitudes, places here even in the United States that we would not consider to be the tropics. So a third definition here, again looking at a range of latitudes once again. And here we're looking at 3 different meteorological or physical quantities. The Coriolis force, an apparent force related to the rotation of the Earth. Horizontal temperature differences, so how they change both in the north to south as well as the east to west directions, as well as horizontal pressure differences, again how pressure changes north to south and east to west at any given altitude for both temperature and pressure differences. So these 3 are all relatively weak within the tropics. So what are the implications of this? Why might all of these be weak ultimately? So again, if we go back to our first definition, the sun is nearly directly overhead in the tropics, however we define it, throughout the entirety of the year. So there is a constant or nearly constant amount of sunlight that is coming in to the Earth in these latitudes throughout the year. And so given that that amount of radiation is a strong control or a strong influence on the surface temperature, that means there's just not a lot of variability in terms of the surface temperature, whether that is in space, north, south, east, west, or throughout the course of the year. If we think about this in terms of horizontal pressure differences, recall from thickness arguments that you might have learned about in 240 or in synoptic or dynamic for those of you who are seniors this year, that if you have a relatively warm column, you would expect to have relatively low pressures near the surface, relatively high pressures aloft. And the opposite would be true if you have a relatively cold column. Well, if you have relatively warm conditions everywhere, that means that you're going to have about the same pressure on the bottom side of that thickness column nearly everywhere. And then, of course, the Coriolis force, that deflection related to the Earth's rotation, is actually zero there at the equator, and it's very small overall. So in the context of something like geostrophic balance, which is the balance between the pressure gradient, or the pressure differences, and the Coriolis force, we have two things that are very, very weak, leading it to be very difficult to actually ascribe geostrophic balance to tropical motions, even though we find that it actually works reasonably well. So these have some important implications upon the climatology of the tropics that we'll discuss as we go through the entirety of the semester. So let's take a look at a fifth one, based here off of the climate zones of the world. So this is again a range of latitudes, in this case characterized by what we would call a tropical climate. Looking at the Köppen climate classifications here at left, we're looking at the A climates, the moist tropical climates, where there's warm temperatures all year round in all of these climate classifications, and either a single wet season, where we have AF, the rainforest, or AM, the monsoon climate classifications, or separate wet-dry seasons, the AW tropical wet-dry climate classification. If we take a look at this map here, we note that these AF and AM, which are in these dark green, kind of bluish, grayish green that we see here, are all located very near to the equator. Indonesia, or what we will call the maritime continent throughout the entirety of this course, equatorial Central Africa, and the northern parts of the Amazon, northern South America here. So these are all places very, very close to the equator, whereas the tropical wet-dry is generally just north and just south of that, so somewhat higher latitudes further away from the equator. We'll show later on in this series of videos, as well as later on in the course of the semester, that where precipitation is maximized tends to move north and south with the seasonal cycle as you go from local winter to local summer and vice versa. So these wet-dry locations tend to be wet in the summer and dry in the winter, whereas near the equator, where the sunlight is nearly constant all year round, it tends to just be wet within that very warm, very moist environment. So there's no specific range of latitudes that we would ascribe to this particular definition. In fact, we see that this tropical wet-dry extends pretty far north in Southeast Asia and even into the Caribbean, whereas in Africa we get into the Sahara Desert at similar latitudes. Likewise, it's a little bit further south in South America than it is in Africa, as well as Australia here, before getting into deserts of the southern portions of those continents as well. So there's no one specific definition, but this is one that you could consider to be more of a physical or a dynamically based definition than something that's a little more ad hoc, as described earlier. So we can also consider the definition of the tropics to be related to the overall circulation within the tropics. This kind of ties in pieces of several different of the definitions that we have already considered to this point in this lecture. So in this definition, we define it as a region where there's tropospheric ascent, so rising motion from near the surface all the way toward the tropopause, easterly boundary layer flow, so we're looking at near surface winds that are out of the east and directed toward the west, which I guess, in your context would be something like this. And then lower surface pressures, so very low pressure near to the surface associated with that warm tropospheric column that we described a few slides previously, with a meridional circulation. So we use this word meridional quite a bit here in the first part of the semester. So that's related to a meridian, which is a line of constant longitude. So when we talk about meridional, we're talking about a circulation that is in the north to south direction, centered here near to the equator. So in this context, the schematic here, we have the equator, the 0 degrees latitude line depicted here. We have relatively warm conditions given by the red shading near the equator that then goes toward yellow and then eventually to green as you get to higher latitudes, indicating colder conditions further away from the equator. So you get relatively low surface pressures here near to the equator, and we know that due to friction, that causes air to converge into areas of low pressure. Where it's relatively cold at higher latitudes, here we have 30 degrees north, down here we have 30 degrees south, we have comparatively high surface pressure. And we know that due to friction, air diverges out of areas of high pressure and then converges into areas of low pressure near to the surface. So here we have our clockwise turning winds associated with anticyclones in the subtropics around 30 degrees north. And so they turn clockwise, but they also spread out from that area of high pressure. Likewise, if we have an area of high pressure turning counterclockwise in the southern hemisphere, it's turning counterclockwise but also spreading out. So we get these winds out of the east converging near to the equator. We call these trade winds because they are often associated with trade or shipping routes dating back hundreds of years as you go from the Old World, Europe and Africa, to the New World in the Americas. As these winds converge near the surface at the equator, when air comes together near the surface, it has to go somewhere when it collides. It can't go down into the surface because that's a rigid boundary, so it needs to go up. So it's forced upward until the point that it can no longer go upward, which in a relatively warm, moist environment like we see in the tropics, is usually most of the way up toward the tropopause. So we get this large ascent near to the equator throughout the entirety of the year. And then when it hits the tropopause, that's kind of like another rigid boundary. The air that's rising becomes very stable once again. And so it spreads out, in this case toward the north in the northern hemisphere, and toward the south in the southern hemisphere. And then likewise, due to the Coriolis force, this deflects off to the right, so toward the east at upper levels in the northern hemisphere, and then in the southern hemisphere it deflects to the left, also to the east in the southern hemisphere. And so we get this overturning circulation here with low-level flow toward the equator in both hemispheres, rising motion near the equator, and then flow moving away from the equator near the tropopause in both hemispheres. This circulation that we've defined here is what we will call the Hadley cell, named after its originator or its inventor. And we'll consider that more in the next couple of weeks ahead in the semester. So having discussed a few of the definitions that we could consider for the tropics, we now want to place this into a little bit broader of a context. And so we focus again on our climate zones of the world, and as we discussed before, there are three major climate classifications for the tropics. We have our rainforest, monsoon, and tropical wet-dry classifications. And as noted before, they're all persistently warm throughout the year, and they differ primarily in how rainfall is distributed throughout the year, whether it's constant or nearly constant throughout the year at a relatively high value, like we see in the Amazon and in the maritime continent, as well as portions of Central Africa, or if it varies more substantially through the year, with dry seasons generally during the winter months and wet seasons during the local summer months. So like there are three different climate zones in the tropics, there are also three major controls, things that govern near-surface air temperatures within the tropics. Our first one is the annual net radiation budget, which we depict over here. So this is another repeat of a diagram that we saw earlier on in this lecture. Again, we have a net surplus of radiation. What is coming in and is absorbed by the atmosphere and surface exceeds what is going out and is lost to space. Whereas here at higher latitudes, that becomes a deficit. What is going out is exceeding what is coming in and being absorbed. While there are heat transports, that Hadley cell that we just introduced is one of the major factors that helps to transport this surplus of heat to higher latitudes to try to mitigate against this difference here. There nevertheless is still more heating near to the equator and less heating at higher latitudes. So consequently, it's relatively warm near the tropics, in the tropics. And given that this red line is relatively flat here within the tropical latitudes, it's pretty consistently warm across the entirety of the tropics. However, there are other important controls, one of which is the surface type, land versus water. And we'll go into a little bit more detail about that on the next slide. We also have considerations related to surface elevation, which we'll go into more detail on in a couple of slides. So again, near surface air temperatures, when they're averaged throughout the year, tend to vary meridionally or north-south with that annual net radiation. So it's warmest near the equator and cooler at higher latitudes, on average throughout the year. Now that's not to say that it can't get warmer at higher latitudes on any given day than it is at the equator. We've seen days of 90, 100-degree weather here in Wisconsin that would have been warmer than it was seen on the equator that day. But again, we're looking at longer term averages over the course of an entire year. And it's certainly not warmer here than it is there. So here we have a map of the Earth, and we're going to take a look at that second factor, that land versus water here. So the equator is roughly where I'm bringing my mouse across here, going through the maritime continent, central, sort of South Central Africa, and the northern parts of South America here. We have portions that are land masses, northern South America, Central Africa, and islands in the maritime continent. There's also a lot of water that we see along the equator. Land and water have very different specific heat capacities, which is a measure of how much energy it takes to change their temperature by 1 degree Celsius, or really by a specific amount, but we're just usually considering that to be 1 degree Celsius. In general, land has a lower specific heat capacity than does water, such that land temperatures warm and cool more rapidly than do water temperatures. We see that here in Wisconsin with regards to Lake Michigan. As we get from winter into spring and summer, while we start to warm up here on land, the water remains very, very cold. That's the originator of cooler by the lake. It takes a lot of energy over many months to be able to warm the lake temperatures up to a relatively high, comfortable value. Whereas as we go from summer down toward winter, we cool off on land much more rapidly than we do over the water. And that can often give rise to lake effect clouds and lake effect precipitation. So it takes a lot more energy loss from the water to the air above to be able to cool it off than we see over land. Now this factor is particularly true for drier land surfaces, and things that are near the equator are all relatively moist, so this isn't really a factor right there. But as you get toward the deserts of central Australia or the deserts of the Sahara in northern Africa, this becomes a bigger factor. Desert soils, very sandy soils, have very high heat capacities. They change temperature very, very rapidly compared to other soil types like clay or even rock, silt, things of that nature. Whereas very wet soils are more like water in their ability to change temperature. They're not as slow in terms of their temperature changes as water, but they're not nearly as fast as you would see for sandy, drier soils either. So sticking here with this map of the world, we have the color shading over land masses depicts the terrain height, where you have the greens, dark and light, indicating places that are closer to sea level, and then the yellows, oranges, and even some of the grays indicating very high locations relative to sea level. Most of our tropical land masses, especially those near the equator along this line that I'm drawing with the pointer, are close to sea level. However, there are a few exceptions. Here in the northern Andes Mountains, the Ethiopian highlands in eastern Africa, as well as some of the isolated mountains here in the maritime continent. We also have, on the fringes of the tropics, the southern extent of the Rocky Mountains into Mexico, the entirety of the Andes Mountains in western South America, higher terrain here in eastern Africa, and then of course the Tibetan Plateau and the Himalayas across southeastern Asia. In general, temperature decreases as you go up. So places that are at higher altitudes, just like we see in the mid-latitudes, like the Rocky Mountains, the Appalachians, and otherwise, as you go up in elevation, the temperature tends to be cooler, whereas places down towards sea level, the temperature tends to be warmer on average. However, we will find, especially in terms of the monsoon circulations of Africa that we will talk about, Asia, that we will talk about a little bit later on in this class, heating of these elevated terrain locations, in that case the Tibetan Plateau, can be very important for driving tropical and subtropical circulations. So even as they may be somewhat colder on average than lower lying locations, they are nevertheless important in terms of governing the circulations of the tropics. So as we start to wrap up here, we want to take a look very briefly at this annual range of surface temperatures. So this is defined as the average temperature on the warmest day of the year minus the average temperature on the coldest day of the year. So this might be the average temperature on a day in mid-July minus the average temperature on a day in mid-January, give or take. And we find that here along the equator, we have a lot of this white shading, which is less than 2 degrees Celsius. So that means that the warmest day of the year is no more than 2 degrees Celsius warmer than the coldest day of the year. Whereas as you go toward higher latitudes, especially over land, as we see here in Africa, the Middle East, and Southeast Asia, Australia, Southern Africa, Southern South America, and then here into Mexico and further up in North America. As you go to higher latitudes in the northern and southern hemisphere, this annual range becomes much, much larger, exceeding 10 to 20 degrees Celsius, so about 20 to 40 degrees Fahrenheit on average, which makes sense. Our warmest day of the year here in Wisconsin usually has an average temperature somewhere around 80 degrees, with a high in the 90s, a low in the 70s, give or take. But our coldest day of the year has an average temperature somewhere around 0, high in the single digits above, low in the single digits to around 10 degrees below 0. So we get about a 70-degree temperature difference, whereas down toward northern Mexico, Florida, that difference is not quite as large. And then near to the equator, it's very near to 0. In fact, if we were to take a look at the high temperature on a given day minus the low temperature on a given day in the tropics, that range would be larger than 2 degrees Celsius. So there's more variability from one day, or sorry, within a day, than there is from one season to the other in terms of surface temperatures, especially over the oceans, but even over land very near to the equator. And then the extent to which that is true changes, decreases, as you go toward higher latitudes in both hemispheres, especially over land, somewhat less so over water. So this concludes our first video of 3 here in the Tropical Climatology or Climatology of the Tropics series. As we go into the next one, we'll take a look at the circulations of the tropics, from which we will then dive into the existential theme of this class. Diabatic heating drives tropical circulations. But for now, that's it for this video.